Hi everybody. In this lesson, I'm going to talk on elasticity. A lot of basic concepts of elasticity can be talked about with a figure like this, taken from a recent textbook by Pollard and Mattel. A rubber band is stretched by a weight. The initial shape of the rubber band is here, with two circles drawn on it as a marker. The circles are stretched into ellipses. First, we understand the concept of strain. The strain is defined as the change in length divided by the initial length. Second, we can revisit the concept of stress. Here, the force is provided by this dumbbell. Force divided by the area of the cross-section of this rubber band gives rise to stress. If you imagine that there were another layer of this rubber band instead of just one layer, then the cross-section will be doubled and the stress will be half. So the strain will be also reduced to half. So really, it's stress that's relevant, it's not the force. Third, stress is linearly related to strain. The higher the stress, the higher the strain. And that is related by the elastic stiffness of this rubber band that is called Young's modulus. Fourth, even though there is no horizontal stress, there is actually a horizontal strain. See, the horizontal dimension, the diameter of this circle, will establish 0. And in the deformed state, this is reduced. So there is negative elongation in the horizontal direction, even though there is no horizontal stress. And that is the concept of Poisson's ratio. In fact, there is not only just a horizontal strain, there is also strain in the direction perpendicular to this page. So the rubber band is actually thinner after deformation. Finally, if the stress is further increased, eventually the rubber band will break, so fracture develops. In this simple diagram, we revisit many concepts here: strain, stress, elastic stiffness, Poisson's ratio concept, and eventually the elastic limit. We're going to talk about these concepts briefly in this lesson. So linear elasticity relates stress and strain by the Hooke's law. When a sample is deformed, strain increases and the stress increases in them as well. The horizontal axis here is strain. The vertical axis is stress. The initial state of the sample is stress-free and strain-free. The state will plot at this point. When the sample is stretched under tensile stress along its axis, strain increases and tensile stress increases. That's this red line. The slope of this line is the elastic stiffness. If the sample is compressed, stress is negative along the axis of the sample. Strain is negative. Again, it's a linear relationship, and the slope is elastic stiffness. So just to summarize, strain can be extension, positive, or contraction, negative. Hooke's law states that stress is linearly related to strain by stress equal a coefficient multiply strain, and the coefficient is called Young's modulus, named after Thomas Young, who first described this material constant. As the bar is extended, by extension it actually shrinks in the horizontal direction, even though there is no horizontal stress, and that is due to Poisson's effect. To further talk about the definition of Poisson's ratio, a cylindrical sample is deformed elastically by tensile stress along its axis, so there is strain in the axial direction. Even though there is no horizontal load, there is actually a horizontal strain due to Poisson's effect. So the horizontal strain, lateral strain, is the same in all horizontal directions. It's a change in the diameter of this sample divided by the initial diameter. And the ratio of the lateral strain to the axial strain is called the Poisson's ratio. So Poisson's ratio is defined in an uniaxial experiment. So in an uniaxial experiment, the uniaxial stress divided by the Young's modulus gives the uniaxial strain. Horizontal strains are due to Poisson's effect. Negative sign is here. It's because if the axial strain is positive, the horizontal strain will be negative. So when you stretch a bar, it shrinks in the direction perpendicular to the axis. If we extend this to a three-dimensional deformation, see the bar is deformed under triaxial deformation, but the stress are still acted upon along the coordinate axis. Then the strain in the axial direction is this. You have to subtract the effect due to Poisson's ratio. You can write epsilon 2 in a way also like this, in which case epsilon 2 equals sigma 2 divided by E minus Poisson's ratio divided by Young's modulus. Here would be sigma 1 plus sigma 3, and you can write epsilon 3 similarly. So we can organize the strain and the stress using this format, writing them as a matrix. Stress matrix, strain matrix, that's a relationship for triaxial stress situation if the stresses are parallel to the coordinate axis. If the principal stresses are not parallel to the coordinate axis, which is the usual case, then we can do a coordinate system transformation of this, and the general form of strain and stress is like this. There are other ways to write this relationship. A common way is to separate deviatorial stress from mean stress, in which case a deviatorial stress tensor will be related to the deviatorial strain by a coefficient G, which is called shear modulus. Shear modulus is related to Young's modulus and Poisson's ratio by this formula. The mean stress, the diagonal summa of stress tensor sigma 11 plus sigma 22 plus sigma 33. So sigma kk is related to the volume strain epsilon kk by a coefficient 3k. K is called the bulk modulus. So for isotropic materials, normal stresses and strains are coupled by the Poisson's effect, but shear stresses are not. So in isotropic materials, sigma 12 only relates to epsilon 12, whereas the normal stresses like sigma 11 is not just related to epsilon 11. It's coupled. It will relate also to sigma 22 and sigma 33. That's what this statement is about. So for isotropic materials, there are two elastic constants, either Young's modulus, Poisson's ratio, or shear modulus and bulk modulus. There are other possible combinations, but the point is that there are only two independent constants. Different pairs of constants can convert to each other easily. Like here, if you use Young's modulus, Poisson's ratio, that two constants can be converted to shear modulus and bulk modulus easily. So two material constants for isotropic materials. Some numbers of Young's modulus and Poisson's ratio for rocks. So rocks, silicates are strong, quartzite particularly strong. The Young's modulus can be as high as 70 gigapascal. 1 gigapascal is a billion pascal. Granite can change greatly depending on its internal texture and structure, so changes from 10 gigapascal to 70 gigapascal. Limestone is pretty weak, can be very weak. It can be also strong depending on its texture. Poisson's ratio in rocks generally varies between 0.1 to 0.4, so a typical number is like 0.25. If a material is truly incompressible, that is, its deformation always conserves volume, the Poisson's ratio will be 0.5. But rocks are usually between 0.1 and 0.4. In anisotropic materials, stress-strain relationships are more coupled. In most general formulation, every stress component is related to every strain component. For instance, if we think of one stress component, sigma 1,2, in isotropic materials, sigma 1,2 is related to epsilon 1,2 only because it's a shear stress. In anisotropic situations, sigma 1,2 in the most general case is actually related to all the strain components. So it relates to sigma 1,1, sigma 1,2, etc., until sigma 3,3, 9 components. So there are 9 elastic coefficients for a shear stress. In materials with symmetry, many of these components will vanish. In the highest symmetry material, like isotropic, there will be only 2 non-zero elastic constants. Every stress Ij is related to all the strains by coefficients. So here we're using again the Einstein summation convention. Repeated indexes imply summation over that indexes. So this really means this. See here, the coefficient forms a tensor. It's a 4th rank tensor because it has 4 indices. And the C is called the stiffness tensor. The Hooker's law can also be written in this form, expressing strain in terms of stress. And the coefficient is also a 4th rank tensor. In fact, it's the inverse tensor of C, and that is called the compliances tensor. We use M to stand for compliances tensor. In many textbooks, S is used. We do not use that notation because S is used for entropy tensor later on in this course. The stress-strain relationship is often written in this tensor form. So stress is C column epsilon. All faces bold, standing for tensors. The column here stands for double index contraction of tensors. Although C has 81 components, M has 81 components as well because it has 4 indices. One indices varies from 1 to 3. So the range of 1 indices is 1 to 3. The total components are 3 to the power of 4. There are 81 stiffness components. However, at most, only 21 of them are independent. This is because of symmetry. First of all, both strain and stress are symmetric. Because of that, there is this symmetry for the stiffness tensor. And also, stiffness tensor must have this symmetry. And this is because elastic materials have a quantity called elastic energy. The existence of elastic energy function in the material requires this symmetry. Because of this, at most, there are only 21 independent components. So depending on the symmetry again. Isotropic material, 2 independent constants. Cubic material has 3 elastic constants. Triclinic minerals, like most feldspar, will have 21 elastic constants. Quartz requires 6 independent elastic constants. So because most minerals are anisotropic, therefore the rocks will be anisotropic in general. Quartz is anisotropic. Quartz grain requires 6 elastic constants to describe its elasticity. When we are dealing with a rock made of quartz, quartzite, if the quartz grains are statistically random in the quartzite, then the overall elasticity for the quartzite might be regarded as isotropic on the big scale. However, rocks usually have preferred orientations. If the quartzite has a foliation, like this case, the quartz grains have preferred orientations, then the elastic property of the material will be anisotropic. So most rocks must be expected to be anisotropic rheologically. Treating them as isotropic is a simplification, and that simplification may be reasonable for some problems, but not for all problems. For instance, if we model fabric development, such as the formation of quartz CPOs, the rheological anisotropy will get stronger as the fabric develops. So the modeling cannot be self-consistent unless we consider this developing rheological anisotropy. So rheological anisotropy is not something we choose to deal with, it's something we must deal with for certain problems. So we've been talking about many elastic equations. The first equation is equilibrium equation, which is written as shorthand here. That stress must follow this equation. This is a universal requirement. Strain must come from a displacement field to ensure that the strain is compatible. And finally, the relationship between stress and strain is described by Hooke's law. That's the rheology. Combining these 3 equations together, we get an equation which is written in shorthand here. It's called Navier equation. So an elastic problem eventually boils down to a mathematical problem of solving the Navier equation. So we solve for the displacement field. Once we know the displacement field, we can get the strain field using this definition. And knowing the strain field, we will be able to know the stress field from the Hooke's law. Solving that is called the solution to a boundary value problem of linear elasticity. We are not going to get to any details of the solution of linear elastic problems. It is sufficient to know the following points. First, the solution of boundary value problems generally requires numerical efforts. Only under simple conditions, simple geometry and boundary conditions, will analytic solutions be possible. A very powerful way of solving boundary value problems is the green function method. We are not going to talk about the green functions method in any detail, but this method is a unified approach to solve a lot of elastic problems, and it is fundamental in the solution of Eshelby's inclusion problems, which are pivotal to the development of micromechanics. That's it for this lesson. Thank you for your attention.